Chapter 6, Part 7, Carbocation Rearrangements. A carbocation rearrangement is a bond shift that turns a less stable carbocation into a more stable carbocation. There are three different types of carbocation rearrangements that we'll see. The first one, and probably the most common, is the hydride shift. Remember that hydride is equal to a hydrogen atom with an extra electron. The methyl or alkyl shift, and also ring expansions, which are a type of alkyl shift. So first, let's take a look at the hydride shift. So in our first example here, we have a molecule that is very likely to undergo an SN1 reaction in the presence of a weak nucleophile. So in this example, we're going to have the bromine leave, leaving behind a secondary carbocation. I'm not going to draw the bromide right now because we don't need it to demonstrate the hydride shift. Now, looking at the secondary carbocation, secondary is pretty good, but remember that our preference of carbocations is tertiary, is better than secondary, is better than primary, which is much, much better than a methyl carbocation. So anytime that you form a carbocation, you should always ask yourself, is there a possibility that I could make a better one? And in this case, we can. If we take the hydrogen with the two electrons that form its covalent bond, and we take this whole thing and slide it over, or rather in curved arrows, take these electrons, put them here, what we would end up with is a molecule where the carbocation has shifted to the carbon that originally had the hydrogen. So we can put little labels on here, A and B. Carbon A used to have that hydride, the hydrogen and the two electrons, but we moved it over to carbon B, which also has another hydrogen atom on its own. And so carbon A is now positive. Now, what's the benefit of doing this? Well, we went from a secondary carbocation to a tertiary. So this is an improvement. This is a more stable carbocation, and this hydride shift is very likely to occur in a substitution reaction, or any reaction that forms a carbocation intermediate. Okay, in our next one, we have an alcohol that has been protonated. And this is a perfect example. The water will leave, leaving behind a secondary carbocation. Well, on the two carbons that are adjacent to it, there are hydrogen atoms. How do we know where this might shift to, or if it's going to shift at all? We're going to label these carbon atoms. So if we were to take one of the hydrogens with its electrons from carbon C and shift it over, we would end up creating a primary carbocation on carbon C. Primary carbocations are not particularly stable, so that is really unlikely to happen. But if we take the hydrogen and the two electrons from carbon A and shift it over to carbon B, we end up with another hydrogen atom on carbon B, so remember there was already one on there, and a carbocation on carbon A, which is now tertiary compared to our previously secondary carbocation. So this shift would also occur because it would create a more stable intermediate. The methyl or alkyl shift is very similar. In this situation, the iodine would leave, leaving behind a secondary carbocation. Now, there are no hydrogens except for on the methyl group next to it, and we know that we don't want to create a primary carbocation. That would be worse than secondary. But next door, on the quaternary carbon, we do not have any hydrogens. Instead, what we have are methyl groups, and those can shift just as easily as a hydride can. Let's go ahead and label these as well, carbon A, carbon B. So what this gives us is a new framework entirely, carbon A and carbon B. Here's the methyl group that was shifted to carbon B. Carbon A is now positively charged because it lost the electrons that had been holding that methyl group onto it. So now it is positively charged. And again, we went from secondary to tertiary. So this is a good carbocation rearrangement. This is something that would definitely happen in this reaction. Let's look at one more example. In this example, bromine is going to leave. Leaving behind a secondary carbocation. And just like we saw in the previous example, we have hydrogens next door, and we have methyl groups on our other neighboring carbon. Now, if we were to move one of those hydrogens, we would end up with another secondary carbocation. A carbocation rearrangement does cost energy. So going from secondary to secondary is not a good energy payoff, and that would not occur. But moving one of these methyl groups would again allow us to create a tertiary carbocation, and that payoff definitely would occur. So this moves our carbocation to the carbon that lost the methyl group, which is this one here. So again, we went from secondary to tertiary. Now, our other type of carbocation rearrangement is the ring expansion. This is a type of alkyl shift. So let's go ahead and remove our bromine. So there are two possibilities when you look at this molecule. You could take this methyl group and shift it over. And what that would give you would be a tertiary carbocation. That is definitely improvement. We're going from secondary to tertiary. But there's another option that we can do with this carbocation here. Let's grab a different color of ink. We can actually take this ring and open it up, because right now we have a 5-membered ring. But if we were to expand the ring, we can actually create a 6-membered ring. And this can be kind of difficult to imagine, so let me draw the 5-membered ring really nice and big real fast. So we have our carbocation. If we want to do a shift that looks like this, that means that we are going to be breaking this bond. So we're going to end up creating a new ring that goes from here to here and then encompasses all of this. So that is going to be a 6-membered ring. The easiest way to draw your new structure is probably just to go ahead and number all of the atoms that are going to be in your new ring. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I know based off of my image here that carbon 1 and 2 should have a methyl group on it. Also, I made a new bond between 6 and 1 with my arrow, and I broke the bond between 6 and 2. So 2 is where my new carbocation is. Now take a look at this carbocation. It is still tertiary, but something else really good happened. We took our 5-membered ring, which is pretty stable, and we turned it into a much more stable 6-membered ring. So this carbocation rearrangement is the one that is much more likely to occur because it is tertiary and a 6-membered ring versus a tertiary 5-membered ring.